Okay, let's solve a number theory question now. This question appeared in the Pre Regional Mathematics Olympiad in 2019. In the Pre Regional Maths Olympiad, the students will have 3 hours to solve 30 questions. So let's see what this question says. The question asks us to find the number of positive integers less than 101, which cannot be expressed as a difference of squares of two integers. So this question initially looks kind of easy, and it is easy, but probably in the high stakes of the Pre-Regional Maths Olympiad, the students may not be able to find a quick solution for this one. So let's define an integer. Let's say n is our integer, n is a positive integer, and let's say n is also less than 101. So since n is an integer, n plus 1 and n minus 1 will both be positive integers. So what have they asked us? They have asked us for the difference of squares of two integers. So I can just define a k. Let me use a different color, I don't want white. Let's say k, and let me say k is n squared minus n minus 1 whole squared. And this is what they've asked us because n is an integer and n minus 1 is also an integer. So solving this will just be n squared minus 2n plus 1, which is n squared minus n squared plus 2n plus 1. And the n squares cancel out, and you can just see that our k will be equal to 2n plus 1. Now this may look familiar because you know that 2n plus 1 is just a representation of an odd number. So now we know that k is an odd number, and also we have established that so we have defined k as the difference of the squares of two integers, and we've established that k is odd. So now following from that, we should know that k does not belong in our solution set, because our solution set consists of positive integers which can't be expressed as a difference of squares of two integers. So we've just eliminated all odd numbers from our solution set. So following from that, let me say there's another possibility here. Let me say that m, let me call this as m, and let me define it as n plus 1, which is an integer, minus n minus 1, which is also an integer. So let me just solve this. N squared plus 2n plus 1 minus n squared minus 2n plus 1. So this will just be n squared plus 2n plus 1 minus n squared plus 2n minus 1. So here you can see that the n squareds get cancelled and the 1s also get cancelled here. So what we are left with is m is equal to 4 times of n. And again, this is just another way of saying that m is a multiple of 4. Multiple of 4. So we have defined m as the difference of squares of two integers, and we've found that m is a multiple of 4. So again, m cannot exist in our solution set because our solution set consists of only the numbers which cannot be expressed as the difference of the squares of two integers. So there are a lot of possibilities like this you can consider. Let me just consider a few more possibilities. Let's say something a is equal to, let me take n plus 1 the whole squared, or let's say we've taken n plus 1, let's take n plus 2 the whole squared minus n minus 2 the whole square. So let me take n minus 1 first. So a would be equal to n squared plus 4n plus 4 minus n squared minus 2n plus 1. So this is just equal to n squared plus 4n plus 4 minus n squared plus 2n minus 1, and the n squares get cancelled, and you can see that a is equal to 6n plus 3, which is just 3 times of 2n plus 1. And we've already seen that 2n plus 1 is odd, and you know that 3 times an odd number is just an odd number again. So a is just an odd number, and we already know that odd numbers cannot exist in our solution set. So let me take one more example. Let's say not a again, let's say b. Let's say b is equal to n plus 2 the whole squared minus n minus 2 the whole squared. So let me just quickly solve this. N squared plus 4n plus 4 minus n squared minus 4n plus 4. And you can see that the 4's get cancelled and the n squares get cancelled, but I'll still write this out just to be sure. That's actually a good practice in mathematics always. Minus n squared plus 4n minus 4. And the 4's get cancelled and our n squares get cancelled. So what we are left with b? We are left with b is equal to 8 times of n. And 8 times of n is again twice of 4 times n. And we know that 4 times n is again a multiple of 4, which cannot exist in our solution set. So b also cannot exist in our solution set. So what we have done is, let me just get some more space here. We have established that whatever combination you take, any combination it will result in either an odd number or a multiple of 4. So it's either odd or a multiple of 4. So neither of these can exist in our solution set. So we can now finally define our solution set as, let us say something s is equal to, there are 100 possibilities because there are 100 integers, 100 positive integers up to 101, excluding 101. So what are we removing? We are removing 50 of those because 50 of those are odd numbers, and as we have seen, odd numbers can't exist in our solution set. We are also removing, first I'll ask you, how many multiples of 4 are there between 0 and 100? The answer to that would be 100 divided by 4, which is 25. So there are 25 multiples of 4 from 0 to 101. So we have to remove those because they cannot exist in our solution set. And why am I removing this? Because it's a multiple of 4. So finally our solution set will turn out to be s is equal to 100 minus 50 plus 25, that's 75. So finally our solution set is s is equal to 25. Not a set, let me say the number of elements. So let me go back to our question. So the number of positive integers less than 101 that cannot be expressed as the difference of the squares of two integers are 25. That's how many we have.